All right, so I'm going to be talking about earthquake-proof buildings. So let's start this off. So some general facts. What do people use for earthquake-proof buildings? They may use flexible foundations, damping, vibration deflection technology, shear walls, cross braces, diaphragms, and moment-resisting frames. You can see here in the first photo that is a vibration deflection that is a use of vibration deflection technology. So let's say there's a house on top of those little dampenings and springs. Those springs would absorb all the kinetic force that the earth would be moving to make the building move less. They could use dampeners. My photo's kind of hiding it right now, but it's basically like a spring, but it's more hydraulic, not hydraulic, but kind of more like that. So yeah, it would absorb all the forces that would be used from the earthquake. Shear walls is basically just a part of the wall that's a very, very, very strong um, thing to then absorb much more load than just a normal wall. It provides lots of strength and it stiffens the building. You can use cross braces, which you see here are basically pipes or pieces of metal that go diagonally across the roof to absorb lateral forces. They may use diaphragms as well, which is a solid roof to move over top that will also absorb forces. Uh, and also moment resisting frames, which is just lots and lots and lots of frames that are ready to absorb all of the forces that come within. So part two, um, earthquake impulses, what they are. So they are random impulses that are created by the earthquake, and they are assumed to be comprised of a number of superimposed impulses. They might be very big. Um, Frequency and motion. The frequency of motion is directly related to the energy of oscillations. So just energy from the earthquake gives off a frequency, and those frequencies go through the walls of the building. Seismic waves. These waves are also propelled through the building to then they will actually be the ones shaking the building at a certain frequency, as mentioned before. So, resonance. The definition of resonance is a phenomenon that is created by external forces or a vibrating system around it to vibrate with greater amplitude at a specific frequency. So, let's say, for an example, a group of tourists walk on a bridge. The bridge can break apart at a synchronized if everyone walks at the same footsteps at a certain frequency. This happens because the bridge has a certain frequency that it cannot withstand the resonance of it. Um, One of the examples is the Tacoma Bridge collapse, where the frequency of the air matched with the frequency of the bridge, which then led to its destruction. You can also calculate for it by wave velocity equals wavelength times frequency. One of my favorite examples of resonance is that you use a tuning fork and you hit it with a piece of metal. It'll resonate, and you have another tuning fork beside it that hasn't been tapped with a piece of rock. The resonance for the first tuning fork will make the second tuning fork vibrate, which is quite cool. So energy conservation and storage in the springs. So when an earthquake happens, the spring damper will absorb a lot of the shock. When they get compressed by the movement, the dampers will compress, and that will lead to slowing down of the mass and movement that's being dealt by the earthquake. They will use these because without them, the building will shake a lot during the earthquake, leading to an increased chance of rupture and collapses in the building. You can very easily use the energy total equals energy total, meaning that the energy at the start will equal the energy at the end. From this point on, the dampers not being used to them um, will be in use, and the spring will rise. But once the spring contracts, the kinetic energy will decrease. But let's say friction and sound energy will come out, which won't make the building shake. So that's how they use these. And so, but there are limits to earthquake-proofing buildings. Um, Number one, scale of the earthquake. The higher the earthquake on the Richter scale, the harder it is for these buildings to withstand them. The more shaking they get, the more higher chance the buildings are of breaking down because of building materials, the soil underneath the building, and the lateral load structure of the building. So for building materials, there is a limit on the capacity to withstand movement and forces for each material. Every material has a different strength. Let's say you use aluminum to build a building, it won't be very strong because aluminum isn't as strong as, let's say, steel. Soil condition. You may have a really strong building, but the soil underneath is made out of sand, and then that will not resist a lot of the movements from the earthquake, and the building will start to shake and fall. And also lateral load structures. So by the design of the building, you could use many things like shear walls and the cross beams. If you don't have them, you're going to be less strong. So yeah, there's always limits to how much you can withstand an earthquake. So my Canadian scientist slash company, I picked a guy named Dr. John F. Cassidy. He's the senior research scientist with Natural Resources Canada. He's researched all aspects of earthquake hazard studies. Mainly, he's been mapping along fault lines, mapping the earthquake, generating stress fields, obtaining more accurate earthquake locations, studying what controls local variations in earthquake ground shaking, and mapping earth structure using earthquake waves. All of this data that he collects is all sent to the national codes of standards for bridges, buildings, and dam. Everything that's being constructed, all of his work is being translated to them. Also, a little fun fact, he also teaches graduate studies at the University of Victoria. Yeah, so thanks for watching. And